Okay, today I'm going to show you some algorithms that you can use if you've got a goal-directed agent that is moving around a search space. I'm going to use this search space here, and the algorithms that I'm going to show you to move around this search space are going to be uniform cost search, that's an uninformed search algorithm, and a star search, which is a heuristic or informed search algorithm. Let's have a look at the search space first. We've got a start state, an initial state S. That's the state that your agent is in at the beginning of the search. There are also states G1, G2 and G3. Those are the goal states. Your agent wants to move into any one of those three. And then there are intermediate states which are labelled A through to F. The name of the game is that you've got to move from the start state, S, and you've got to then put together a path that achieves one of the goal states, either G1, G2 or G3. So for example, a path could be that you move from S to D, then from D into state E, and then finally from state E into G3, and that then achieves the goal state for you. However, you'll notice that the movements between states are along arcs, directed arcs that have numbers on them. The number on an arc is the cost of traversing that arc. So for example, to go from S through to state A costs 5, and to go from S to state B costs 9. The name of the game is that you've got to move from S into one of the goal states, but you've got to do that with the minimal total cost on the path. So as I say, I'm going to show you two algorithms for doing that. The first one is uniform cost search. Uniform cost search is basically a variant on Dijkstra's algorithm, and it's going to find for us the cheapest path, the least costly path, between S and one of the goal states. I'm going to use a tree, and the tree is going to encode all the paths that we're exploring at any time. And we're also going to keep a visited list of all nodes that we've already visited, because we won't need to visit them again. And you'll see this happening during the search. So the first thing that we do is we consider the only path that we've got so far, which is just the one that starts and ends in the start state. And we say, does it finish in a goal state? No, it doesn't. So therefore we expand it. And the way that we expand it is like this. We consider all places in the tree that we can get to, sorry, in the graph that we can get to from the start state. And the places that we can get to are A for a cost of 5, B for a cost of 9, and D for a cost of 6. So we write 5 here, 9 here, and 6 here. We now say that this node has been visited because it's been expanded, and we add it to the visited list. So on the visited list so far, we've got S. We now calculate the total cost of the three paths, the three new paths that we've created. So the total cost of this path is 5, total cost of this path is 9, and the total cost of this path is 6. Another name for uniform cost search is cheapest first search. So the way that we do it is we select the path to expand next, which is the cheapest and which is still available for expansion. Well, we've got three paths, and the cheapest one is A, so that's the one we're going to visit next. Let's see where we can get to from A. Well, from A we can go to node B for a cost of 3, or we can go to G1 for a cost of 9. So let's put those in. So we can go to B for a cost of 3, or we can go to G1 for a cost of 9. So A is now visited. We add it to the visited list. So there it is. And we calculate the costs of these new paths. This path has a cost of 5 to go from here to here, and a cost of 3 to go from here to here. So that's a total cost of 8. And this path here has a total cost of 14. Notice that although G1 is a goal state, we don't accept it at this point as being the optimal path. And the reason for that is that the optimal path may well be over here. We have to explore all the paths over here until we're exploring paths of length 14. Then we might accept it. Okay, so at this point in the search, we've got 4 active paths. The one ending in B here, the one ending in G1 here, the one ending in B here, and the one ending in D here. The cheapest one is this one, ending in D. So that's the one that we're going to look at next. We ask if D is a goal node. It isn't. So therefore, we expand it. Add it to the visited list first. When we look at D over here in the graph, we can get to C and we can get to E. And we can also get back to S. But we're not going to add S to the tree. It's already on the visited list. So the only nodes that we add to the tree are C and E. So C goes here and E goes here. And the cost to get from D to C is 2. Cost to get from D to E is also 2. So we calculate the total cost of the path and the total cost of the path here, and we get 8 for both. So there are now 5 active paths in the tree, and at this point 3 of them, B, one ending B here, one ending in C, and the one ending in E, they all have a cost of 8. I'm just going to take them in alphabetical order, so I'm going to look at this one first, B. So we look at the graph and we look at B. Well, from B, we can go to A and we can also go to C. But A is already on the visited list. In fact, it's visited on this very path here. So there's no point in going back to it. However, we can go to C. So we'll put that into the tree. So from B to C is a cost of 1. And so the total cost along that path from S to C is now 9, and B is visited. We now look at the active paths and we find that the next one to visit is C at a cost of 8. We ask, is it a goal state? No, it's not, so we expand it. From C, we can get to G2 for a cost of 5, F for a cost of 7. We can also go to S, but S is already on the visited list, so we're not going to visit S again. So we'll add G2 and F to our tree. G2 and F. G2 will cost us 5, F will cost us 7, so therefore the total cost of this path is 13, and the total cost of this path is 15, and C is visited. Next one to visit is E. It's not the goal state, so we expand it. The only place that we can go to from E is to G3 for a cost of 7. So we'll add that. G3, cost of 7, 15. And E is now visited. We'll add it to the list. Okay, so now we look to see what active paths we've got. We've got 1, 2, 3, 4, 5, 6 active paths at this point. We have 2 of them that have a cost of 9, B and C here. So I'll just take them in alphabetical order. So I'll go to B first. But B has already been visited, and because of the way the algorithm works, it was visited already at a lower cost than on this path. So therefore, we treat that as a dead end, and that's how I'll mark a dead end. Similarly, the next path to look at is this one. It ends in C. C has already been visited. It was visited here at a cost of 8. So therefore, that's a dead end as well. So we now have 4 remaining active paths in our tree. And we have 1 for 13, 2 for 15, and 1 for 14. This is the next one we look at. And we ask, is G2 a goal state? And indeed, it is. So at this point, we stop the algorithm because we've reached the goal state, and we return this as the path that we're going to take through the tree. And because of the way the algorithm works, expanding paths out that are the shortest first, we know that that is the optimal path through the tree.